student from the Biomedical Engineering at Royal Academy. Yeah, and today we are diving into something super cool. But first, have you ever wondered how we can see inside the body without X-ray? Huh? Exactly. Think about something like ultrasound, but smarter. Smarter? How? Oh my god! Well, imagine mixing lights and sounds together to create clear images inside the body. Light and sound? That sounds like it. It's kind of it. It's called photoacoustic. You shine a tiny pulse of light into the tissues, and the tissue sends back, believe it or not. Sound wave. No way. Light copying and sound how much? Yeah. And those sound waves help us to build detailed image of blood vessels, oxygen levels, and even detect early diseases. That's actually amazing. So it's basically light in, sound out, and image. Yeah, exactly. And we are here to show you why photoacoustic is becoming one of the most exciting emerging technologies in modern medicine. Let's get started. Biomedical imaging plays a critical role in modern healthcare by enabling early diagnosis, disease monitoring, and real-time visualization of biological processes. However, no single existing modality can simultaneously provide deep tissue penetration, high spatial resolution, and rich functional or molecular contrast. This unmet need has driven the development of photoacoustic imaging, or PAI, a hybrid modality that combines the strengths of optical excitation and acoustic detection.
And here is Photoacoustic timeline. Back to 1880, Alexander Graham Bell's discovery. He discovered the photoacoustic effect while developing the photophones, a device that transmits sounds using light. He observed that when modulated sunlight hits certain materials, they produce audible sounds. The phenomenon was first called photophonic effects. It's the foundations of the photoacoustic principle. In 1930, early gas analysis, Emil Virgilov applied the photoacoustic effects to create high-sensitivity gas detection systems in Russia. His work shows that acoustic signals generated from absorbed light could be measured with remarkable precision. It's the first practical engineering applications of photoacoustic. In 1973, modern PA spectroscopy. Alan Rosenzweig and colleagues developed the modern theories and instrumentations for photoacoustic spectroscopy. The work made it possible to analyze opaque or highly scattering materials, something difficult for traditional optical methods. The terms of photoacoustics become widely adopted in science and engineering. And 20 years after that, in 1993, researchers produced the first clear in vivo photoacoustic image for a human finger. This milestone demonstrates that photoacoustic signals could be detected safely and reliably in living tissues. It's the proof of concept for biomedical imaging. In 20th century, Leon Wang and others enabled photoacoustic tomography as a 2D or 3D imaging technique that demonstrate functional imaging, including mapping blood oxygen saturations using hemoglobin absorption spectra. Photoacoustics become a powerful biomedical imaging modality. In recently, research evolved toward clinical applications such as breast cancer screening, melanoma detection, vascular imaging, and neural imaging. Efforts now focus on compact device, handheld probe, and integrating PAI with ultrasound. Photoacoustics moved from laboratory demonstrations to real-world medical tools.
Let's describe the photoacoustic concept. First, a short laser pulse, as a near-infrared light, is directed into the tissue. Second, the light is absorbed by molecules known as chromophores. These molecules convert the absorbed light into heat, causing a very small thermoelastic expansion. That expansion produces ultrasonic waves, which are then detected. Finally, the detected signals are then processed to reconstruct an image that shows the tissue structure and blood oxygenation. Now let's first describe the first step in photoacoustic tomography. Absorption in biological tissues, such as the Beer-Lambert law, describe the intensity of the incident light after a given amount of distance, which can be described by the following equation, which I describe the intensity after a given amount of distance inversely proportional to the absorbed coefficient. The Beer-Lambert law is important in describing the limitations of an optical-based system. In this case, the Beer-Lambert law is used to describe the scattering light by replacing μA with the model scattering constant μs. This equation helps describe the scattering in tissues, where μs is around 1 to 10 millimeters in biological tissues. Scattering coefficient is inversely proportional to the wavelength citation. This means that the major part of incident light has scattered after 1 millimeter. Scattering increases with shorter wavelength. This is why near-infrared NIR light is most commonly used in optical biomedical engineering. On the other hand, diffusive optical tomography extends the penetration depth by detecting diffusive photons. This requires complex algorithms and suffers from poor spatial resolution. For biological tissues, to generate high-frequency ultrasonic wave, the incident pulse must be below 1, the thermal relaxation time, and secondly, the stress relaxation time, where DC is the characteristics of dimensions, and the ATH is the thermal diffusivity. Considering a 15 micrometer structure, we can find that thermal relaxation time is 1.4 milliseconds, and the stress relaxation times is orders of magnitude lower than the thermal relaxation time, meaning that the laser pulse needed to be less than 10 nanoseconds to generate high-frequency ultrasounds, which is typical for neodymium doped cantium yttrium doped garnet. Sorry, neodymium yttrium garnet lasers that are around 5 nanoseconds in pulse width. Next, I will describe energy absorption. The PA signals at the instant of generation is linearly proportional to the amount of light absorbed. It can be spectroscopically differentiated between endogenous chromophores. As we can see from the graph, different molecules have different absorption. PA uses these properties of absorption to image spatially. In some photoacoustic systems employ an optical permanent oscillators, or OPO, which are nonlinear crystals to create tunable wavelength. To target specific molecules, OPO is used in spectroscopic imaging, which generates two different wavelengths, the signal and idler wavelength. The two wavelengths can be described by this equation, which follows the rule of energy conservation of Planck's law. Given the equation, 1 over lambda pump is equal to 1 over lambda signal plus 1 over lambda idler, which follows the Planck's law E equal to hv. Another thing to consider in an OPO system is the phase. Phase matching follows the rules of momentum conservation. The momentum of light is the sum described as the sum of final light, the idler plus the signal, plus the another constant k, quasi-phase matching, or QPM, which depends on the choosing nonlinear crystals. In bifrequent phase systems, the k-QPM constant will be zero, meaning no momentum loss from phase matching or phase changes, meaning the signal and idler phases are equally zero, which in quasi-phase crystals, they will contain a QPM constant, meaning that signal and other wavelength will, after passing an OPO, will have different phases, such as in a PPLN crystal. Data acquisition of PA. The sound attenuation can be described as alpha, where A is the tissue-dependent constant and F is the frequency described in megahertz. B, the biological constant, is around 1 decibel per square centimeter megahertz for most tissues, but 20 decibels per centimeter megahertz for bone tissues, assuming that B, the biological constant, is equal 1. This form of attenuation affects more the higher frequency and thus acts as a low-pass filter, reducing overall resolution for high-frequency PA system. Now, ultrasound detection. First, we'll describe the physioelectric crystal, which occurs when resonance of the wavelength of the generated wave is half-length of the crystal Lt. Physioelectric will generate electricity when there is a sound wave passing through it. The resonant frequency can be extracted with the knowledge of velocity of sound, Ct, which gives the following this equation, which is the resonant frequency. Different type of detector designs of physioelectric systems consist of circular and linear systems, or single detector systems. Now the optical based system. Here we describe a photoacoustic interferometer which create fringes due to the change in cavity length. The path difference from A1 to B can be described as the distance from A1 to A2 plus the distance from A2 to B. As we can see from the image, we can derive that the distance of A2 to B is the cosine of 2 theta. We can then derive the path difference of the wave. This is useful for calculating phases at each location of the Fabry-Pérot interferometer, finding where the node and antinodes are present, describing the emittance of each passes, where n describes the number of passes, T and T palm are the amplitude transmission coefficients at each glass plates, and R is the amplitude reflection coefficient of the glass plates. From entering the mirror structure, the light absorbed from the mirror is a function of T and exited as a function of T palm. Calculating the intensity can be obtained by multiplying the transmitted electric field by its complex conjugate. By shortening the term, R 2R over 1 plus R squared to F, which F is the finesse. The transfer coefficient of Fabry-Pérot interferometer system is simply the transmitted intensity over the initial intensity. This coefficient can be described by 1 over 1 plus finesse plus sine squared delta over 2. The width of the transmitted peak is related to the coefficient of finesse. A method of finding the coefficient involves measuring the width of the transmitted peak. The wavelength criterion states that the separation of corresponding two closely separated wavelengths and must be at least full width half maximum, or FWHM, to be able to be resolvable. For the minimum wavelength difference to be resolvable, the equation gives delta lambda min, which is the minimum wavelength to be resolvable.